Hello, you join me live from a bungalow in England's first Hollywood. You'll have to do the looking up. I'm not going to give you any more clues than that. Welcome to the traditional Sunday Science Q&A. We weren't on last Sunday, and that was only because we, on Friday night, we did a lovely event with Tanita Tickeram and Josie Long and Helen Czerski and Samantha Cristoforetti, who is a really inspiring astronaut and many other things as well. Really, so if you haven't caught up with that yet, that was a really enjoyed. I think, still the longest consecutive time for a European astronaut in space, as far as I remember, 199 days. Again, you can check this information yourself. That's what we need to be doing more of. So today's Sunday Science Q&A. It's all doctors, so I won't be using any of that. You would just take it as read that every person on this is a doctor in mathematics, in glaciology, in bubble physics. I know it's not called bubble physics, Helen Czerski, but that's what I like to call it. So just tell you a few things, which is one, if you can support us via Patreon. If you don't support us by Patreon already, that is very, very useful to us, because we're trying to make about 3, 4, 5 shows per week on lots of different subjects. We're trying to keep up with all of the kind of science stuff that we can. We want to make more, and of course our normal resources we basically aren't earning because, for instance, my big autumn tour no longer exists. So it means that if we can get some money in, it makes it easier for us to make stuff. So if you are able to support us via Patreon, thank you very much. If you are not able to support us via Patreon, but you have a small amount of money that you feel should go for our own particular niche. Well, I mean, it's niche in so much as it's niche to be interested in everything that exists in the universe. Then we also have a tip jar at the bottom here, and you can just pop something in today. So today, I'll tell you what we've got going on. We have a new 3-part web series coming up on Cosmic Shambles. The first episode is out now on the YouTube channel, Cosmic Shambles YouTube. It was filmed pre-pandemic at the Kennedy Space Center, which Kennedy Space Center for me is where I saw Duran Duran live last year, and also with the actual space shuttle Atlantis, and it's looking at the history and engineering behind the shuttle program and its companion series on the Stand Up Maths channel as well, with Matt Parker looking at the maths of space flight. So and that has all been made possible by our Patreon supporters, so thank you. On Wednesday night I will be different. On Wednesday night, by the way, there will be less content from me on Wednesday night, because this is the last time you'll see me with all of my teeth. I've finally reached an age where one of my teeth is going. I'm having one molar, which, despite me often saying to the dentist, I think there's something wrong with that, he went, no, it's fine. Basically, it's just a hollow remnant of a molar, which is a reminder that Kurt Vonnegut was told by his dentist that our teeth are actually only really meant to exist till we're about 44 years old, which tells us when we should really die, and everything after that is borrowed time. Thank you, Kurt. Your dental optimism is something which preys on my mind a great deal. But we are on Wednesday doing a Doctor Who show and tell, and other things beyond Doctor Who. We have Toby Haydock, who did an absolutely wonderful series, which was on Radio 4, called Moths Ate My Doctor Who Scarf. He does a huge number of events for Doctor Who conventions, and also loads of the DVDs as well. And he has an incredibly encyclopedic knowledge, as does Alan Lear, who you may well have seen on Newsnight talking about when Sharda came out. He, a member of the Doctor Who Appreciation Society, runs some really great Doctor Who conventions with his partner Erica, probably wife Erica, I think. And now that's most of that done. First of all, congratulations, by the way, to our regular co-host on this, Helen Czerski, who is going to be one of the Royal Institute Christmas lectures this year, also with Chris Jackson and Tara Shine. And we're going to have a special announcement next week on next Sunday's show, where we will have Chris and Tara on the guests, and we will talk a little bit more about that. But let's go over to Helen. Hello, Helen. How are you?
I am doing very well. And yeah, it's exciting that there's 3 of us for the first time since 1957, I think, the International Geophysical Year. They had, I think, actually 6 that year, and this year they've got 3, which is appropriate for Earth. Earth science has got lots of stuff in it, right? So it's quite nice to have a team job on this, so we can all cover the different bits from different areas of expertise, which is sort of what you need for Earth science. You know, that thing of single lone heroes going off and doing stuff in science, not really how it works anymore. So yeah, we're looking forward to getting stuck into that.
So how much are we allowed to know? I mean, will they individual lectures, if you're allowed to say, or will you all be kind of working together?
So we will each have one lecture. we're trying to play with it a little bit, but there is nothing confirmed on that yet. But basically, each of us will do. Chris will talk about geology. I will talk about the oceans. Tara will talk about the atmosphere, and it will go in that order. So we are each responsible for one. But we know they weave together, so we're going to try and represent that in some way. And obviously, it's going to be a bit different this year. We don't know how because, well, lecture theatres are not the busy places they used to be. I think that is fair. They will be recorded at the Royal Institution, but the style might be a little bit different. But then that's exciting, isn't it? Something to play with, something to experiment with. And that, they've been going for 180 years and they've been brilliant. But, that doesn't mean you can't experiment sometimes. So we're going to be playing with some of that as well.
There is the one pity about that is for anyone who's ever been behind the scenes at a Christmas lecture, it really is like a circus, isn't it? In terms of the number, I was lucky. I had a small part of having a magnetic pulse to the left hand side of my brain when Sophie Scott did them, and backstage was just people dressed as chimpanzees on stilts, and there were rooks and there were ravens and there were there was a menagerie, and it's a wonderful thing to see how all of your minds coming together to create that kind of science communication. I'm really looking forward to that. What is your show and tell today?
I have this, and I have to point out it's not a urine sample. I realised I probably have to say that straight away. It's a sample of water from the North Pole, and it's got the date on it. So it's the 12th of August, 2 years ago. Now, the reason I'm showing this is that, so this is from when I went to the North Pole 2 years ago on the ship. The reason I'm showing it now is that I have, there's another very, very big expedition ongoing at the moment, Mosaic, where they've been drifting all the time. All the rest of us have been dealing with coronavirus. One German ship has spent an entire year almost now drifting across the North Pole, frozen into the ice, doing science, just kind of following the ice along. And I have friends who are still on it. And one of the things that is you might not expect now, which was new for Mosaic, is that we can contact them during WhatsApp. So there's no pictures, but we can send text WhatsApp messages, which is a bit weird because we're all normally used to people who go away. You don't hear from them for many months. And I'm getting WhatsApp messages from my friends on board. Anyway, so the reason I was thinking about the water was that the situation they're in now is very similar to the one we were in 2 years ago, and yet what they're looking at, in that they're at the North Pole, they're the ship's frozen in and they're doing their studies, but what they're seeing is so very different. And what they're seeing compared with when we were there 2 years ago is that the melt ponds are actually re-melting. So what happens is you get melt ponds during the summer, it freezes and then it stays frozen, and they're re-melting this year because it's so warm. He said it's only just below freezing there at the moment, and one of the consequences of that is that there's lots of algae growing that we didn't see at all. So I saw this pot on my shelf and I thought the thing that was striking about this water for us at the time was that it was so clean, in that there's not a lot living in it. And now I think if the samples that this one friend brings back will probably have a lot more life in them, which sounds like it might be a good thing, but it's a major change to the way the Arctic works. So I was just thinking about my little frozen bit of history here, if you like, from 2 years ago, and just thinking about how much it's already changing. And of course we don't know, there's year to year variability, but obviously this is the general pattern. It's getting warmer there during the summer, and we're trying to study it as it's happening. It's like trying to study it being on a train that is getting into trouble and we're watching it happening. But yeah, so there are big changes already. So I just wanted to show you my little pot that is definitely not a urine sample.
Brilliant. You've said that too many times now for us to believe that. We're also joined by Dr. Katie Steckles, who I think I was trying to remember because I did so many. I've just been doing a show on Radio 4 called Laws That Aren't Laws, and I did Parkinson's Law and Murphy's Law back to back. And Parkinson's Law and Murphy's Law have a certain amount of kind of overlap. You did Parkinson's, didn't you?
Yes. Yeah.
Good. That's what I was trying to remember. I was trying to remember whether it's yes. So, which was a bit of really great input as well in terms of the mathematics of that. Now, Katie, as a mathematician, I think you have something. There's actually had to be a bit of setup for your show and tell, which always excites me. So there's a level of drama and show to this.
Yeah, I've gone slightly complicated. There might be multiple cameras involved. Essentially, I wanted to show and tell this, which is a little thing that I was given as a gift last year. But it's the kind of thing that you might find in a second-hand shop, sort of a vintage item. And if I take it out of its little case, it's got a little kind of vinyl case that it comes in. But it is an adding and subtracting machine. So it says across the top here, adding and subtracting machine. And this is the Admaster Junior. So it's junior. I guess you could presumably get a more senior version of this. This one I think does something like 10 digits. So I guess the senior one maybe has more digits. But the idea of this is that you can use it to do addition. And I guess this is the kind of thing that was popular before calculators became a thing. But it's a really simple kind of setup. So you can kind of input numbers here. So say I wanted to put in a number 4, I just put my little stylus in at the hole where it says 4 and slide it all the way down. And then the little hole at the top should now say 4. And if I wanted to make, say, 24, I put a 2 in the next column and slide that down, and I've now got 24 set up on here. But of course, this is an adding machine. You want to see it doing some adding. So if I want to add something to that, I could say do 24 plus another 3. So I go in at 3, slide that down. That's not hugely impressive. It's just made that 4 into a 7. But what you really want to see is if I now try and add, say, another 6, right? What's going to happen? Because we're going to go bigger than 9. It's going to be weird. So I pull it down as far as I can, and it comes up with a little red arrow in the hole, which means go all the way up and over the top and down. And what that does is it kind of goes over this little notch at the top and pulls the next column down 1. So it increments, it kind of carries the 1 across to the next column. And I got this, this is a really nice little thing. You can obviously do that all the way across. And these come in lots of different versions. So I think some of the early companies that made these were German. Ones of these with German writing on. But I've seen one that's got pounds, shillings and pence. Like there's all kinds of them. You might be wondering about the fact that it says adding and subtracting up here. Well, that's on the back. So on the back here, it does subtraction and it's got all the same things set up and you can slide those around. And it's got this little bar at the top. If you pull it out, it resets everything to 0. So it's a really nice little kind of self-contained thing with a little holder for the stylus. And I was inspired by this because I like sort of playing around with things and I sort of wanted to see how it works, like what's going on inside this thing. So I may have very carefully with a tiny screwdriver prized the cover off this to have a look inside, took loads of photos, made sure I could get my head around it and then carefully put it all back together and knowledge to build a slightly bigger and stupider one, which is obviously the correct thing to do in any situation. So if we could switch to the other camera, you might be able to see I guess you might be able to see this is the wooden Admaster, I guess. This is the version that I've made, and this is very much a prototype. So this is just kind of 3 bits of MDF that I've laser cut and kind of put together, but it does all of the same things. I've made a little wooden stylus for it, so you can put the thing in here and make that down into a 4, and I could make it into 24, and then I could add another 7, and I'll get to there, and it gives me my little red arrow, and then I go up and over, and it's 31. And the nice thing about this is I can take this apart. So if I remove my carefully applied bulldog clips that are holding the whole thing together, you can see what's going on inside. So if I take off the cover, it's just really simple. It's just a series of things that slide up and down. And the way that the kind of notch thing works is that if I put, you can see there's a little gap here between bits. It's probably easier to see if I take one of these out, but there's actually a little gap there. And if I want to go, say, up and over, I would put my stylus in here, slide it up, and that would be where it hits the top, and then I just literally go across to the next column and slide it down 1. So the whole thing just works within this sort of sheet, but once you put the front on, it kind of holds everything in the right places. Sadly there isn't a reset mechanism on this. I haven't managed to build that in yet, but this is a prototype, because basically what I would like to do with this is build a massive one. Like, I'm imagining the kind of thing you could come and visit at a science festival where it takes up the whole side of the room, and you've got, like, instead of a little stylus, you've got like a broom handle or something that you stick in the thing and pull the things down. Because I'd really love people to be able to sort of get hands-on and interact with this. But I've got my tiny little Admaster that I can use to do my own little calculations. And I think it's a really nice little vintage piece of calculating equipment.
Has it got a date on it? Do you know when yours was made?
I don't know. It'd be really nice to know. The kind of the cover, most of the writing's worn off it. I can see that it used to say Admaster, but it may have had more information on in the past. But literally, it was found in a second-hand shop by a friend of mine. But I've seen a few of them, like correntator, I think is another word that you see for them. And they definitely do addition and subtraction, but you sometimes get slightly more complicated ones that do clever things as well.
That's brilliant. What a wonderful thing. I would imagine many people who were watching this are now currently just scurrying through the internet to try and find their own one. That's fantastic. Thank you, Katie. And our final guest today, Sammie Buzzard. How are you?
Hi, I'm good, thank you.
Now, you are a glaciologist. It is glaciologist, isn't it?
Yeah, that's right.
Good,
Yeah.
good. The because it's a glaciologist. So there's a whole Broadway show tune to be made from that, obviously. What is your show and tell today?
Okay. Oh, I should say before, within our field, I've had very senior scientists say glacier and glacier, so I wouldn't worry. We get both. We haven't decided ourselves, so it's no wonder everyone else doesn't know. So my show and tell, I panicked slightly when I found out I was going to have to do a show and tell for this, because I'm currently working in the US. So I moved out to Atlanta, Georgia in January of last year. And unsurprisingly, with everything that's been going on this year, I've not been home so much since then. So I have my 2 suitcases of things, most of which were boring practical things like clothes. So I was like, what on earth am I going to show them? But then I remembered I was lucky enough last year to go and visit NASA Goddard Space Flight Center up in Maryland, where I spoke to lots of people there who cared about ice and frozen things, because NASA's obviously most famous for all their cool space stuff, which is amazing, but they also care a lot about Earth observation, and a lot of the reasons that we know what's going on in the polar regions is down to NASA and the European Space Agency having satellites up there and monitoring those areas. So it's a really cool place. I was genuinely shocked by how little security there is once you're inside. So it's obviously very hard to get into the NASA complex. I had to get lots of permissions. And once you're in there, all the live mission areas, you obviously can't go near those without very, very high security clearance. But there are lots of areas that are just these big warehouses with random bits of rockets strewn around that people have kind of just started working on and have been left there, which I could have spent weeks there just walking around seeing all these bits of space junk everywhere. But one thing I also did while I was there is I met Claire Parkinson, who is a very senior sea ice scientist. She's one of the pioneers of sea ice science, really. And that was super cool for me because it's not that often you get to see very senior women scientists, especially in kind of physics areas. So that was a great day. But not only that, she gave me a book. So best day ever. Who doesn't need more books? So my show and tell is this here. I'm hoping this will come out over the camera. But this is Arctic sea ice. If you can see the dates from there, from 1973 to 1976. And we can see all the maps they made of Arctic sea ice back in the 70s. So this was the real kind of dawn of the satellite era. We weren't regularly monitoring the polar regions at that point. And the thing that I found most interesting about this book, other than there being lots of cool maps of sea ice, which is enough to keep me excited for quite a long time, there is really no mention at all of climate change in this book, because this is, of course, the 70s. And what makes communicating climate change really difficult is the fact that we know that we're warming up the planet. When you hear the words like anthropogenic climate change, that's us, that's humans. We're warming the planet. There is no doubt about that. But there are also lots of other things happening, especially to the Arctic sea ice. There are natural cycles, there are storms. Some years it's warmer, some years it's colder. So if you only have a few years of data, so here we've got 73 to 76 in this book, you're not going to pick up that signal of things warming and the ice changing. There's enough variability that they wouldn't have looked at this data and thought, oh yeah, we're definitely losing the sea ice. It wouldn't really have stood out from those 4 years. Now, when in 2020 we have a really long record of sea ice, it's really obvious. But I found it pretty fascinating that not many years ago, atlases like this were being published, that we could talk about something like sea ice. Now, if you mention sea ice to anyone today, they'll say, oh, it's melting, right? Anyone, even in the general public, that's been on the media enough that people know sea ice is changing. But in the 70s, even though we had this amazing satellite technology, we didn't yet have the data to know that it was changing so much.
Fantastic. Thank you very much for showing us that. Those are great show and tells. An excellent start. We're going to get straight into the maths now. This is, so Katie, we'll start with you. This is from David Emery. Did we discover or invent mathematics? So this becomes quite a philosophical question, I would imagine, as well, to some extent.
Starting easy there, yeah. I mean, happy with just, what's 8 plus 12 to start off with. But yeah, okay. Yeah, I think this is one of the big questions that people ask, because this sort of philosophical divide between whether maths is something that, is entirely a fabrication of humans, or whether it's something that sort of just exists out there in the universe and we're kind of uncovering it gradually bit by bit. I think I personally, I don't know if it's a thing you can have an opinion about. I think my personal opinion is that it's more discovery, because I like this sort of romantic idea that there's all this wonderful stuff out there just waiting for us to go and dig it up. But I think there definitely is some aspect of it that is sort of about the way we do maths, I guess. If you kind of reset everything back to the beginning and ran humanity over again, would we discover maths in the same way? Would we find things in the same order? And I think it's probably a mixture of both, because there are things which are kind of fundamental constants. Like if you've got prime numbers, say, they'll always be interesting. They'll always have that same property. No matter how you come to them, you'll discover that this thing exists. So Pythagoras' theorem, the square on the hypotenuse is always going to be equal to the sum of the other two sides on a right angle triangle. And at some point in the history of your society, you'll discover right angle triangles and you'll discover this fact. You might go about proving it in different ways. Something like Pythagoras' theorem, there are a lot of ways to prove Pythagoras' theorem, and you might find a different set of them if you were to try again from the beginning. I suspect a lot more of the applied math stuff would be done in slightly different ways. People would find different ways to approximate things and, different ways to make use of the maths. But I think the really pure stuff, the kind of really abstract mathematical kind of ideas, would be the same regardless. So I think those kinds of things are discovered, but then the way that we make use of maths is something that we invent.
I loved it. We had Brian Greene on a while ago, and I did a book Shambles with him. His new book's wonderful, actually. Highly recommend it. But I loved it. At one point, he said, sometimes I have these moments of fear where I imagine the extraterrestrials arrive and they go, oh, yeah, we used to think maths was the language of the universe, too. I thought it's quite delightful. The next question is from John, and John would like to know, in fact, this is a maths question, so I hope you don't mind, Katie. I'm going to go straight to her. What makes a good and in fact, this, I think everyone else will have something to say about this, because it's also about modelling as well. What makes a good mathematical model? Is the design of the model more important than the data included? For example, if you have great data, can a less great modelling system still provide useful results? Sure if you,
Yeah, I think it's a tough question, because I get how good your model is depends on how good your data is in some cases. Like a lot of the time you inform how the model works by looking at the data. I'm very much a pure mathematician, so this is on the more applied side, and not the kind of thing I usually play around with. But my understanding is that if you've got a brilliant model but not very good data, like it doesn't necessarily, you kind of need both. Basically, you need a bit of both to contribute to it, to actually have something that's meaningful and useful. And any model is only as good as it is. You can't rely on them 100%. So it's the sort of thing, like the more complicated your model is, the closer it will approximate the thing that you're trying to model. But in fact, eventually you get to the point where it's so complicated that you might as well just run the universe and measure everything. The point of making a model is to simplify it enough that you can calculate it yourself, and any simplification is going to remove data.
But there's a really interesting combination of ideas here, which is that the model is the machine and the data is what you feed into it. So I see them as two separate things. Like you can build an extremely realistic model of physical processes, for example, what's a cloud doing, when's it going to rain, all that kind of stuff. But that machine of your model only does something if you put in some initial data that says, well, today the temperature is 20 degrees and it's definitely raining over here. And the data kind of feeds through the model. And so they are separate things. You do need them both to be right. And there's two things that the thing that really is interesting here is the question of sensitivity, because all models, like the real world, some things matter more than others in the hierarchy of things that matter. And so it may be that perhaps the temperature really, really matters. So if you get the temperature wrong by even a little bit, your whole thing will be off. But maybe some other parameter like humidity, well, you can get that wrong by 10 or 20%. It doesn't make that much difference to the outcome. So actually what you do with models is you tune them so that they deal with the most sensitive data, and they're most accurate where it matters, where the temperature matters most. They really deal with temperature in a lot of detail, and some other stuff is slightly, it's kind of penciled in rather than done in fine detail. And so there's this really interesting thing between models and data. And so the time when it matters, we shouldn't have the whole lecture on this, but the time when it matters is that what if your starting assumption was wrong? What if you thought, well, perhaps, the warm water under the Antarctic ice sheet doesn't matter very much. So we'll design a model that says, oh, that bit doesn't matter very much. So your initial data might not be good enough. And then you find out, and then you've got to go, oh, no, we do need to build a better bit of the model, because now we've got data that says that does matter. And so there's this although I think the model and the data are very separate, it's the machine and the food. You design your machine depending on how important the food is. And yeah, but we're constantly trying to improve these things. So it's always a bit of both.
Yeah, you do very much need both the models and the models to be good with all the physical processes and the data. It made me laugh when Katie said you can build a brilliant model and have rubbish data. Because I was like, oh, she's read my PhD thesis. Because working in the polar regions, we don't have a ton of data to work with, surprisingly. People don't go there that often. We don't have a lot of information. But one of the problems we're starting to come up against, now that we're getting more and more data, there are more satellites. NASA launched their ICESat-2 2 years ago now, so we're getting tons of data in, more than we can currently work with, is how much computing power do we have to work with this data. So I, for example, look at lakes and rivers on top of Antarctica, and I model those on quite a small scale, and by small scale I mean meters or kilometers. But people who are worrying about the whole global climate will be looking at degrees of latitude and longitude, so they can't possibly incorporate the processes that I'm looking at into their models. So we have to make a compromise. And again, what Helen mentioned about sensitivity, we have to decide which processes are most important that we put into those bigger models now. And hopefully, as time goes on and we get better computers, we can put in more and more processes and get more accurate models. But computer power is very much a limiting factor as well in that.
But there is something another sort of add-on to that, is that if you go to the satellite data centers like Copernicus, which is the big European satellite, those constellations, the Sentinels, they produce loads of data, and they are designed to produce more data than any current computer can deal with. They don't expect computing to catch up with that amount of data for another 20 years. But because once you've got better computers, you can't go back in time. You need the best resolution data now. So they're hoarding it, even though they're not expecting to be able to use it for another 2 decades, which is brilliant and a bit scary.
Yeah.
Now we've got, go on, Sammie.
I was just going to say one thing that is good about those is that we kind of can go back in time, because once we know how things in the climate have changed, we can use that past data to test our models. So if we have data from now and in 10 years' time we build a model, we can start this model in 2020 and say, what does it think happened in 2030? And we can see if it gets it right. So that's also really exciting, that you can test the models, then you have more trust in their future output and what they're saying might happen to the world in the future.
Brilliant, thank you. Katie, your next question. This is a high-pressure one, because this is settling a bet between brothers after an unsatisfactory answer from Hannah Fry. So I'm not putting any pressure on you here, but this is Rob Eng says, I asked this when Hannah Fry was on, and she didn't really give a conclusive enough answer to settle this long-standing dispute with my brother. So I've been waiting patiently for some mathematicians. Graphs are charts, but charts aren't graphs. True or false?
Oh, that's an English question, I think. That's that's more about definitions of words, isn't it, I guess? So what the thing that throws a spanner in for me is that graph is a word that mathematicians also use to describe a completely different thing, which is a sort of network diagram. And I guess that's what I would think of if you say graph. But I think people do use that to mean like a line graph. I guess chart is also used more generally, so you get things like flow charts and org charts as well that are charts. So I suspect that
charts. Nautical charts and air charts.
Yeah, well, exactly. Yeah, maps are charts, aren't they? And it's also a term that's used in maths to describe something that looks at a small section of a surface. But anyway, words are words. They're used for lots of different things. I suspect that there is an overlap between graphs and charts, but I couldn't necessarily say that one is fully included in the other. It's maybe a Venn diagram with a non-empty intersection.
So are you telling us you can't draw a chart to tell us whether the charts and graphs, what the relationship between charts and graphs is?
It's a diagram. It's neither. Yeah.
Oh, well, this is good. So anyway, Rob, if you and your brother are ultimately bonded by the fact you have this continual dispute, much like the Hitchens brothers, of course, always were, then the dispute remains, and therefore your bond remains as well. So I think that's good news. But I'll tell you what, we'll wait. The next time we've got an English graduate on the Science Q&A, then we'll also throw it over to them as well, and we'll see where we get. This is from Brannigan's A. And Sammie, I don't know if you know this. This is there the same amount of water on Earth as there was a few million years ago, just in different forms?
I don't know as far back a few million years ago, but certainly the way that the climate system works at the moment, then water is constantly changing between water vapor, ice, and actual water. So definitely in kind of recent history I'm talking in terms of thousands of years rather than millions, then yes, we do have the same amount of water. It's just in different states and it's constantly changing.
Excellent. Thank you. Now, definitely for you, Helen, because it's about bubbles. This is from Eileen Chang, who would like to know, where can you find anti-bubbles in nature, or are they all man-made? And do anti-bubbles produce sound at their formation and or when they collapse like bubbles do? So if you could first of all just define what an anti-bubble is for us, Helen.
Well, I should start by saying an anti-bubble is something that I didn't know about for quite a long time. And then a student of mine who had a project came to me with these photographs and said, there's this thing here. And I'm like, that's a weird thing. I don't know what you've done there, but that's not a thing. And he was like, it's here for a photograph. I want to study it. Like, okay. And it turned out he was right. And and you can tell, you can identify bubbles very quickly. So an anti-bubble, imagine, so I'll tell you what it is by the way it normally forms. So imagine you've got a drop of water that is falling down onto the surface of some other water. And as it falls down, there's a little layer of air underneath it. And the drop goes down and the little layer of air stays. And then the water closes over the top. So you've got your original drop in the middle with this shell of water around it, a shell of air around it, and then water outside of that. And so it's like a soap bubble, but inside out, basically. It's a shell of air with water on the inside and water on the outside. And it sounds like it shouldn't last any time at all. And actually, they can last easily 30 seconds, the big ones, up to several minutes for the really small ones. And they are stable. And so they're a bit tricky to make, but you can do it. And I think they will form in nature because you can imagine, first of all, it helps have some surfactants. So you need a soapy surface, or there's lots of natural surfactants. So there's lots of organic matter in, the natural world that will generate a layer of surfactant. So I reckon if you had water, like rainwater dripping off a leaf from quite low down, you would get one of these forming, and then they sit just under the water column. And one of the odd things about them is that they don't rise, and of course, not very quickly. And the reason they don't is that there's so little air in there that it can't move all the water that's on the inside. They do rise eventually. So you can identify them first because they're perfectly spherical, and most bubbles kind of squash as they get to the surface. They look a bit squashed because of buoyancy. And secondly, anti-bubbles just sort of drift around in the water column and look really odd. So he was right, and he did a study on it over the summer, and then together we wrote the paper that answers the second question here, which is, do they make a sound when they're formed? And bubbles do generally make a sound when they're formed, because at the moment that a new bubble forms, it's usually got an edge. It's usually got a sharp bit. Bubbles don't like sharp bits, so that pointy bit of the bubble basically springs back, and it's like a hammer hitting a bell. Now, anti-bubbles don't make very much sound at the moment they form. So when the drop goes through the water and the water closes over the top, there's very little noise. But what happens when an anti-bubble pops, right? It's underneath the water, and eventually the air drains up to the top and it touches at the bottom. And then all that air that was around the outside goes whoosh and makes a new, smaller bubble that is a proper bubble. And that makes a sound. And you can record that sound, and you can actually measure how thick the anti-bubble is by measuring the sound that it makes when it's destroyed. So that is a very technical answer, sorry, but they're really interesting. They are very hard to form. They were first seen back in 1922, and then nobody thought about them. And now they're actually used for medicine quite a lot. So really tiny ones, because you can put little blob of medicine inside this air bubble, which you can then make stable. So quite a lot of the research on them now is for really, really tiny anti-bubbles that people are using for drug delivery. So they're really interesting little things. And I think they do form in nature, and they make a sound when they're destroyed, but not really when they're formed.
Brilliant. Thank you. And just a reminder for everyone, if you do have a question, by the way, you can actually just write them up now, put them on the feed. And we have got a lot to get through, but we may well be able to squeeze a couple more in. So if you have anything on maths, on bubbles or anti-bubbles, on climate change, then get them in now. And also a reminder that if you can go down to the bottom of the page somewhere and you'll find a tip jar if you fancy putting any money in for today's show, or if you, on the longer term, go to Patreon and subscribe to us there. That will be very useful to us, and we thank you very, very much. But also, of course, if you don't want to do that or you can't do that, that's not a problem as well. We always try and make as much as possible free to access. So let's now, this is from Melissa R. Katie. She would like to know, is the hunt for the biggest prime number real world useful, or is it more just a fun mathematical problem?
I mean, to be clear, the biggest prime number isn't going to be a thing because they do go on forever. That's the thing we definitely know. There is strictly no biggest prime number, but I guess there is a new biggest prime number every time a prime number is discovered that is bigger than all the previously known ones. So I think generally what happens is that because it's difficult to find prime numbers, right? The important thing is that there is no pattern in the prime numbers that we can discern. And if we could, believe me, a lot of mathematicians would be very pleased about that. If we knew how to predict where the next prime number would be, that would be a very useful thing to know. But because prime numbers are random in a way that isn't like any other kind of randomness, it's not something that we have a handle on really. So if you want to know whether something's a prime number, you just have to take that number and divide it by a bunch of stuff and check. And there are a few other sort of shortcut ways of doing it, but generally it's quite difficult, computationally difficult, to determine whether something's prime or not. So when they're finding big prime numbers, they're not just kind of going to the next biggest number that we don't know whether or not it's prime and just checking that one. They're doing sort of shortcut things like using Mersenne primes, which are prime numbers that are next to powers of 2, I guess, and you check the numbers that are next to powers of 2, and there's some kind of shortcut methods for doing that, which means the top 10 biggest prime numbers, certainly recently when I checked, were all of this form. So kind of we know a bunch of sort of smallish prime numbers, tens of thousands of digits, and then there's a few that we know that are above that, but they're all kind of quite spread out. There's a lot in between that we don't know about. To answer the actual question, I think having big prime numbers, because big prime numbers are used in things like encryption, and there are useful things that you can do with them. But in practice, the most useful aspect of it is going to be that in finding these numbers, you'll develop techniques, you'll understand things about prime numbers and about number theory and about even just how good your computers are, that will improve maths otherwise generally anyway. So it's sort of useful in the sense that it furthers mathematics because people are thinking about interesting things and trying to find new ways to solve these problems. But finding the actual numbers themselves potentially to some extent might be sort of stamp collecting, but prime numbers are cool, so it's good to know where they all are.
Brilliant. There's a question for you, Sammie, from Renee, who would like to know, there's something that is probably simpler than it seems in my head. What's the difference between a glacier and an ice flow or iceberg, or are they just different words for the same thing? So again, kind of definitions of trying to understand the picture that you can place in your head.
That's a great question, actually, because a lot of people don't know the difference. So the easiest one is a glacier or an ice flow is something that is essentially ice on top of land. So the kind of glaciers we have up in the Alps count. Antarctica is kind of lots of glaciers and ice flows all mixed up together, sitting on top of the land. And when we get an iceberg is where one of those glaciers or ice flows meets the sea and part of it breaks off. That is your iceberg. So ice that used to be on the land and is floating in the ocean is an iceberg. Now, this is different from the sea ice I was talking about earlier, because that's the frozen ocean. And that's another thing that people often find confusing, which is understandable. It kind of is. So most of the Arctic is covered in sea ice, which is something completely different. As for the difference between glaciers and ice flows, that's kind of less clear. I tend to think that ice flows are bigger areas. Glaciers are kind of smaller areas going in a certain direction, whereas ice flows...
I think there's a spelling thing going on here, because the problem is that it's difficult, is that there's two words, there's F-L-O-W and F-L-O-E. And I think what Sammie is talking about is the W version. And the thing that is the frozen sea ice, when they become really big, when those frozen platelets, then we would call that an F-L-O-E, ice flow. So the ice flow with a W is part of a glacier, and the ice flow with an E is very large sea ice.
Right.
And it does make it difficult because people say the word and everyone has one of those versions in their head, but they often don't check which one it is.
Yeah, because that was asked about the with a W, but of course we don't know if in fact it may well have referred to something that has been heard in conversation. Yes, let's stick with these kind of various different etymological problems that may well occur during the day. This is about zero, nothing, and its existence. Yeah, get ready. This can go to any of you. If in physics an empty space still is something, in that nothing is something, is mathematical zero the only true nothing, or is zero still something? Now, this is quite all of you, I'm going to throw this up because this is a very, I think from the moment that people start to, if you add up everything in the universe, you end up going, and it's zero. It's, what happens when you get zero? If you smash open nothing, it turns out it creates a lot of something. That's where I think people there's so many different ideas of the true existence of nothingness. So, starting with that, I'm going to go to you first, Helen, because you're the physicist.
So I think this very you are of a practical or theoretical mindset. So nothing, I would say, is a theoretical concept. And it's very useful because it's a theoretical concept. But in practice, because of quantum fluctuations, you could argue that zero is never actually reached. So I think if you like playing with ideas in your head and it's very useful, then you would probably tend towards zero being a theoretical construct. But it is, I don't know, I think it's really revealing. It says more about the people than it does about the maths. I think, there's that joke that there's a load of jokes that say, a building's on fire, an engineer walks in and throws a blanket over it, and the physicist walks in and does something else, and the mathematician walks in and says there is a solution and walks out again. Sorry, Katie. But it's that sort of thing. I think there's a zero, and if all you care about is that in the theoretical world, the maths, the beauty of the equations works that way, then I think you like your theoretical zero. I'm a practical person.
Well, can I ask then, is there anywhere in the universe where nothing exists?
There's always energy, right?
Yeah.
That's where we get to the and gravity and field. So the definition of a field in physics is something that fills all space, and it is the case that a field could have a value of zero, but it's always going to be a slightly non-zero value because of quantum fluctuations, whatever the field is, I think. And it is weird. Yeah, physicists use this word field, and everyone's got this mental image of a thing with cows in it. But actually, a field is just a physics word that says something exists everywhere through all of space. It's not a physical thing. It's not, you can't pick it off the shelf. But that's our way of describing something which conceptually it exists in every bit of space that there are. And so you can have all kinds of different fields. But I think the field always has a value, even if that value is effectively zero. It's still there. I don't know. What's the mathematician say?
Well, I mean, that's the thing. Kind of, there are results about that things, are equal to zero at certain points. Like there's a really nice and stupidly named bit of maths called the hairy ball theorem, which says that on any hairy surface, so essentially a vector field on the surface of a sphere, there must be a point where it's equal to zero, and it's called the hairy ball theorem because it's sort of roughly equivalent to you can't comb the hair on a ball flat. Which is why people always have a bit of hair that sticks up at the back if you cut the hair short. But anyway, I think zero as a sort of mathematical concept. I mean, I almost feel like to say that it is the true nothing is sort of doing it down, because zero is a really important and useful concept, and it's an abstract concept, but in the same way that 5 is, right? It does exist, it has an existence and a meaning. And there are senses in which zero is sort of nothingness. So, for example, in the context of adding zero doesn't change the thing you've got. So in that sense, it's sort of a nothingy thing. But it's important that it exists because you need to be able to say what happens. If you do +1 -1, what does that mean? But if you think about zero and multiplying, then it very much does make a difference. If you multiply something by zero, it will kind of eliminate it. So, it's a concept and it has lots of properties, but in the same way that almost any other concept in maths does. And, it is special. It's not just like any other number, but a lot of numbers have interesting properties, and zero is just one of them, I guess.
Now, Sammie, you're in a position here where you can either decide to answer the zero nothing question, or you can opt out and go straight for one about satellites and climate tracking.
I mean, one of those is definitely more. So maybe we should go for the satellites.
Okay,
I'm
an
applied mathematician, so zero for me is just a nothing, and I don't question that too much.
Oh, well, good. You've answered that anyway. Great. That's so now. This is from Ethan, who would like to know: are satellites getting so good at tracking climate that there is reduced need for field work in locations that might be environmentally difficult, damaging to go to?
I can see Helen laughing there. She's suffered some time.
Go on, Sammie.
Yeah, well, the thing about satellites, it's great. We're getting more measurements and more regular measurements, but we need to know that the satellites are correct. So we still need people to go to all these difficult to reach locations and do something which we call ground truthing, which essentially, if we're trying to work out, for example, how much snow is on top of a sea ice floe, FLOE, we'll go with that one, we need someone to actually go there and dig it up and stick a ruler into the snow and say how much snow is here, and compare that to what the satellite said to check that the satellite is right. So we're still going to have to go to these places. We just get more data in between those trips to the places from the satellites.
But there's also something which is much bigger. Sorry, I will make my soapbox stint here short, which is process. Is that what a satellite never measures the thing you get out of it. That is not what a satellite does. What a satellite does is measure some property of radiation of a form of light, and then you interpret that. But what it doesn't tell you is what's actually going on. And the reason I feel strongly about this is that I am a process scientist, right? I'm the one that's on the ground or on the ocean looking for the small mechanisms. And I'm actually involved, in a couple of things at the moment where there's this big idea for a satellite mission, which could do all these things, but actually it can only do anything useful if you already understand the bits of the engine that are actually happening in the surface of the ocean. Like, if you go a meter below, what's happening? What's it doing down there? Because it's only when you understand that you can go back to the satellite data and go, okay, maybe this is telling me something useful. And the thing about the natural world is that the processes are so complicated that if you're not checking all the time, you risk just assuming that you understand from the satellites. And one of the reasons I care about this is that what I see is earth science, there's a danger of earth science becoming a load of people basically playing computer games, which is that they've got some computer models, they get some data, they muck around in this virtual world and it all looks fine, and then they tell us that's what it means. Whereas if you go out into the environments as a field scientist, you experience stuff, you notice things that were never on your list of things to notice. You see things that aren't supposed to be there, and you see that some of the things that are supposed to be there aren't there. And unless you're constantly doing that, you lose your reality check. You're just playing computer games. And I think it's really important that scientists go into the field and really physically understand what it is they are studying, even if they only do it once because they hate going on ships or up mountains or whatever.
I 100% agree with that. It's something that in glaciology really bugs me, is I feel we're very separate, the modelers and the field scientists. And I think to be a good modeler, which is the box I put myself in, I still need to have been and seen some ice occasionally to know what's going on, because there are things that are surprising. And to be able to work best with the people who are out in the field all the time, we need to know what kind of stuff they're going through, getting that data, to know how to use the data well. So I think we should have a lot more overlap for sure.
I remember a discussion a few years ago, 10 years ago now, there was a big ocean project, and the Office of Naval Research in America had brought the experimentalists and the modelers into the same room, and they were having an argument about how much light there was 2 meters below the ocean surface. And this theoretician just said, it got quite heated, he just said, look, why can't you just measure what the light is 2 meters below the surface of the ocean? And the experimentalist said, well, it's because the surface of the ocean is going up and down by 10 meters. Like, you tell me exactly what in that you consider 2 meters to be, because you've got this conceptual idea that looks very simple, and then there's these practicalities that make it quite a lot harder. So yeah, but we all need to talk to each other more. That's the lesson, isn't it?
This is a question from Rachel. This is for all of you. Rachel says, have any of you spent days trying to work out some exciting new phenomena and then realised it wasn't new at all, and you just forgot to do something simple like carry 2-3 pages of working out? So she says, I regularly do this when coding and it makes me want to cry.
I wish I'd only spent days doing that, to be honest. The total time of my career so far is a number I don't want to try and calculate. It happens to all of us, absolutely.
And any particular kind of those moments of going, yes, this is it. This is a new. Oh.
Yeah, I've done that. I've had but the one that I got most excited about, and in my defense, it was because I made some measurements and then I had to go and do other stuff for a couple of months. So I held on to this thing before I really checked it and got all excited for 2 months. And I thought I discovered a new way that bubbles break up and when they're smashed about by turbulence. And it turned out that what the bubbles were doing is they were rising up in my experimental tank and they were hitting glass tubes. And it was basically like a ting, a sort of ting noise when the metal stick hits a triangle. And so the bubbles were making these glass tubes ring. And I was so excited that I thought I'd seen this pattern. And it turns out the bubbles were literally playing my experiment like a musical instrument. And then the excitement went away.
See, the nearest I can have to that is that thing where when I used to be a stand-up and you come up with a joke and you suddenly go, there's no way this joke can't exist already. And you just spend weeks ringing up friends, go, has anyone done this? Has anyone done this? Has anyone done this?
I actually did that last week. So I've actually got to do some science in the middle of all this COVID stuff in the last week. And the last few months, I've been really, I've found a thing to do with how breaking waves do something. And I've been really pleased with myself. I've been reading I'm writing the paper on it, going back through the literature. I found a paper written in 1987 by my postdoc supervisor, where there's just one throwaway line where he was like, oh yeah, and of course you could do this. And I was like, I thought I was first. I thought no one had noticed this before. And he hadn't made the measurement. He hadn't done any of the details, but he had noticed that it was possible in 1987. And I went, oh, okay. Well, at least I've got some numbers now.
Right, final question for today. Oh, actually, one more I should mention, which is someone wants to know, where can they see these anti-bubbles, Helen? Where's the best place to go on the internet to see?
There's very little video of them. I mean, if you just Google anti-bubbles on YouTube, you'll find some people who have made little videos showing them. Don't pay too much attention to what they're saying in a few cases, but they definitely make them. You can see them. The nice way to do it is that you put dye in the water that you drop in, and then you can see there's a little blue blob that's kind of moving around. But actually, try it for yourself. Get a pipette, get some soapy water, and drip them from very low down, and you'll see drops kind of hover on the surface for a bit before they go in. And somewhere around there, if you mess about with drop size and height, you'll be able to make some anti-bubbles.
Brilliant, thank you. And then, yes, Matt would like to know, since we've known about climate change since the 1800s, how have the mathematical predictions and models from then, or as far back as we can go, stood up to where they are now? So, Sammie, in terms of I suppose, first of all, the changing in the possibility of modelling. I mean, that's when do we first start seeing what would be notionally called a model in terms of this area?
Well, anything that they were doing back in the 1800s could be called a model. If you just have one equation with an input and an output, that is the most simple kind of model. The difference is our models now have all these different processes in them. So the original models would just be saying things like, if we put more carbon dioxide into the atmosphere, things are going to get warmer. We have the greenhouse effect. But now we're able to say things like, well, we know things are getting warmer, so how does that affect the ocean? Is the ocean expanding as it gets warmer? Are we melting polar ice caps and putting water into the ocean? So the level of complexity that we have now and the amount of processes that they wouldn't even be able to consider in the 1800s, because they wouldn't even really known about Antarctica to any real extent, we just have so much more information now. I'm not going to say that our predictions are necessarily way more accurate, because there's still... I'm not sure if you could hear that. But we are definitely improving the models all the time. So we still have a long way to go, and we know a huge amount more than we did in the 1800s. But we still have a lot that we still don't really understand, which is why I'm in a job, and it's great.
Brilliant. Thank you all very much. That brings us to the end of today's Science Q&A. Next week, as it is only next Sunday, it's only 98 experimenting days till the Christmas lectures. So we will already be starting our Christmas rundown by having Helen will be back. And we will also have Chris and Tara, who are going to be presenting. All three of them will be doing the Christmas lectures in December. So if you have any questions, not merely on their areas of expertise, but as well about kind of approaching these ideas about how they're thinking about working out ways of.
We're not going to give away too much.
Well, okay. If you've got any questions for them, they won't answer them. There we go. That's changed the Sunday Science Q&A. We can have Sunday A, but you won't know what the Q was because that's kind of keeps it mysterious. But in terms of approaches, without actually giving away, I think that idea, we might talk a little bit about science communication as well. Within that, I should also mention, by the way, that Nora Chamberlain was meant to be on today, president of the Institute of Mathematics, and pretty much at the last minute there was something that's the kind of thing that happens when you're president of the Institute of Mathematics. Suddenly there are major mathematical world issues that come up, and she will be with us, I think, in the next couple of weeks. We'll put that up, but there will be more of that soon. So thank you very much to Katie, to Sammie, to Helen. As I said, Helen will be back with us next week. You can support us via Patreon, or just put something in the tip jar. And also, if you ever kind of think, oh, do you know what, this is a scientist that I'd like to hear from, or a subject that I'd like to hear about, we're always interested in your useful and creative feedback. We're not particularly interested in your negative feedback, because there's plenty of that out there anyway, and most of us have some element of self-loathing, so we can do that ourselves. Thank you very much, as usual, to our producer Trent Burton. As I said, on Wednesday we're going to be doing a live Doctor Who show and tell with two people who know an enormous amount about Doctor Who and have incredible knowledge also of many of the, not merely the actors in it, but the producers, the directors, and the creative people, and a lot of the people working on the technology side as well. So that's going to be with Alan Lear and Toby Haydock on Wednesday evening, I think at 8:30 as far as I remember, and I will have one. I'll show you what happened to my molar. So for those of you who like kind of video nasty dentistry, you can enjoy that and enjoy the moment when a bit of cotton wool suddenly just flies out of my mouth and ends up just landing on the camera. That will be fun 3D stuff. Okay, have a lovely bank holiday Monday, and enjoy as much of your life as you can, I say. Bye-bye.